So today we are here for a climate coffee with Jens Terhaar of the University of Bern. We're going to talk with Jens about the record sea surface temperature jump in 2023-2024. And this was, as in the title of the publication of Jens, unlikely but not unexpected. So if you're here for the first time for this series, just to give you an idea of what we are doing in this series, climate coffees are a format that I've been running on for some years. 2 years with Ocean Eyes before we were with another project. My name is Chiara. I work for the Danish Meteorological Institute, and this format is funded by several European funded projects. So specifically Ocean Eyes, but also the ones that you have seen in the previous page. These are all kind of contributing to the time that we spend here. This is an informal setup so that everybody can actually jump in the conversation after the talk. And it's a format for sharing ideas, building a network, presenting results. And that's why we invited also Jens into this context. It's suitable for all levels of maturity in your career. And if you would like to become a speaker in one of the next climate coffees, we run this format once a month. Reach out to me and we'll be happy to schedule you for the next few months. Normally we take a break between July and August. So we let people go on holiday and then we resume in September. Just for you to, just some housekeeping. I would like you to check if your microphone is on mute. So just do this check for me because it's easier then to moderate the session later. Your cameras are all off, so thank you for this. And normally we run the session this way. Jens has got around 20 minutes for his talk. The presentation will also be shared. The recording will be shared. So if you're missing anything, you can find these references in the documents that I'll circulate later. During the talk, you can also use the chat to type your questions by the time they come up. So this is like a way to do it. And otherwise, we just go into a Q&A after the talk of Jens, and then you can raise your hand so we can prioritize the people just by raising hand, or you can keep on typing in the chat. Now, I will give the floor to Jens, and I will put you in the spotlight so that everybody can see you. Perfect. And Jens, if you would like to share your presentation, this is a good time, and I will still let people in. This is quite crowded this morning, so it's good.
Okay.
Perfect. Thank you,
Perfect.
Jens. I see the presentation. You got the floor.
Yes.
Thank you so much.
Thanks a lot, Chiara, for the nice introduction, and thank you for having me for the climate coffees. I'm happy to present our paper from last year about the record sea surface temperature jump in 23-24. And I will talk a bit about implications for the transient climate response to emissions and also a possibly upcoming warming hiatus. Possibly, not surely. So let's jump directly into the topic, given that it's 20 minutes. So what we have seen in 2023-24 by now is everyone is, I think, aware of this, was a very special event. And the ocean was warm almost everywhere, especially warm. But there are some patches like the North Pacific or North Atlantic being even higher, and you can here see the anomalies that were quite extreme. And it's not just the anomalies, but it's compared to previous years, really how much it exceeded previous anomalies and broke out records. And this is easiest to be seen on these plots from that were online or in the media quite a lot. And each line represents SSTs, or the seasonal cycle of SSTs over a given year. And in gray are the lines before 2023. And you can see they were always a bit relatively close together. And then in 2023, the blue line here, temperatures exceeded the previous temperature bunch or groups of lines. And temperatures became much warmer and stayed there for almost a year, and then started to go down at the end of 2024 again a bit. And when you look at this, it's the separation from the old records was by 0.2 to 0.3 degrees, and globally averaged, so globally from 60 south to 60 north. The jump compared to the previous record was by a magnitude of 0.25 degrees approximately from NOAA data, and this has raised a lot of questions in the media and in the research and academia. So there were a lot of articles, for example, on BBC, that the oceans are suffering from record-breaking heat, And also the question is what's happening? So is something exceptionally happening in terms of variability? Is the system shifting to a new state? Is there something that we haven't been aware of? And yeah, that was addressed in the media, but also in academia. And there was a comment by Gavin Schmidt in 2024 saying that climate models can't explain the huge heat anomaly. And we could be in uncharted territory. And at the time when that was came out, I was still working closely with people from Woods Hole, where I spent a year, and they were always critical about models. And then this came out and was like, see, models can't really do it. And I felt a bit challenged by this because as a modeler, because in this worldview or opinion piece, they didn't really look into climate models, at least not dynamic climate models. What they looked at, that's what you can see here, is more statistical climate models. So they said that given with the general trend, this sudden heat spike exceeds predictions made by statistical climate models that rely on observations. But the headline somehow suggested that general circulation models, dynamic climate models can't do it. And I was challenged by that and wanted to see if these models actually can do it or can't. And this is where then this paper came out that we published in Nature last year. And what we did is we looked into, or we built our own statistical climate model based on observations to see if this event could have been expected and how likely it is. And we also looked into dynamic climate models, so general circulation models, to see if they can simulate such events. And I'm going through this paper now step by step. So first, on the observation-based statistical models. So what we did is we just try to make it as simple as possible, but still having the necessary complexity in it. So we built 100 million year-long time series, and we prescribed the underlying trend, the variance, and the autocorrelation based on observations. And then we just calculated how often we get a jump in SSTs that exceeded previous records by 0.25 degrees. So that doesn't mean we count jumps when temperatures change by 0.25 degrees in 1 year, like this, for example, but really when the old record is broken. So we always look to the old record like in observations. And then, as you probably can guess or know, it's very difficult to estimate variance and autocorrelation and trend from our observations because our observational time period is relatively short. So we tried our best to do this. And to get the variance and autocorrelation, we used ERA5, the Hadley Center SST dataset, and EISST to get data from 1940 to present. And we fitted different curves, third order polynomial, Enting spline, the second order polynomial. So we tried a lot of different things, but the estimates were relatively similar. You have to go into the supplementary material of the paper to see the differences, but they're qualitatively and quantitatively similar. And then we fitted this trend and removed it. And from the remaining time series, which now has no trend, we calculated variance and autocorrelation and not observation-based estimates. And then we also need the trend in the year where the record happened, so in 2023. And for that, we used the NOAA OISST data. There was by another paper that compared different observation-based data sets of SST, judged to be the best available data at that time. But we also compared it to different other data sets. And again, the results are quantitatively and qualitatively similar. And as I said, these estimates have uncertainties just because of the way statistics work and how long our time series is. So these are the uncertainties that we used. We have here warming trends based on our OISST. We have the variance based on the three products with the best estimate in the middle and autocorrelation. And so we, based on statistical foundations, we created these Gaussian curves, and then we sampled. That's why you see these ticks there. We randomly sampled 10,000 times from each of these distributions and got 10,000 combinations of autocorrelation, variance, and warming trends, so that we could see what happens if we have a really large warming trend and a small variance, but also a strong warming trend and a strong variance. And then we built 10,000 time series that each one 100 million years long. And then we just sampled the jumps, and then we got our return period. So this is the probability density function and of the return period. So every how many years do we expect, based on our observation-based estimates, a record-breaking event of 0.25 degrees in the ocean. And you can see that the distribution is quite large, but we get a mean of 512 and a median of 448. So here, but the uncertainty, so the 95% confidence interval goes from around 200 to 1,200 years. And in the most unlikely combinations, it's even possible that the return period is much higher, but it's not possible that it's lower than 120 years approximately. So this is just based on purely on warming trends, variance, autocorrelation, and observation-based estimates of these. But it already shows that even if we use statistics of observations, assume large uncertainties, it's not impossible that something like this might happen, but it's a very rare event. So 1 in 500 years is just very unlikely. And then what I found most interesting is to look into climate models and see if they actually can simulate these events. And this is what we did afterwards. So here you see again this time in monthly means, the SSTs from the observations. Here's one model from the CMIP6 archive. Here's one model from our GFDL ESM2M simulations in Bern, Switzerland. And here's one model from the CSM large ensemble. So in total, you can see that we got 270 simulations to look at. And in each of these simulations, we found events where SSTs broke the old record by at least 0.25 degrees. So this is basically the first message, that models can simulate these events and can simulate such jumps, and in years that are relatively close to the jump where it happened in the observations. And then we wanted to see how extraordinary or how high could it get in models. And this is where this plot comes into play. So what you see here is that each dot is a year where SSTs broke the old record. And then on the y-axis, you can see by how much the old record was broken, so the margin by which it was broken. And the dots are colored to see the different ensembles, but it doesn't really matter from which ensemble they come from. And the crosses are the observations. So each of these cross means that in the observations, an old record was broken. And then we have here 2023, where the record was broken by 0.25 degrees and where we had this extraordinary event. What we can see is that it's really at the limit of what we can expect from models. So there are models that are in this order of magnitude, but there are really not many, and we are hitting the high point really of what is expectable, or what based on models and what models can simulate. And we also counted in the models because we had 270 simulations, and if we wanted to get years with a trend approximately similar to the observed trend, but still enough years to sample from. So we took the 20 years before and 20 years after, more or less, so the time from 2000 to 2040. And we see that we get 11 jumps that are at least 0.25 degrees, or break the record by 0.25 degrees. So that would correspond to a return period of around 1,000 years. But also, given that it's a lot of years of data, but it's simulation model data, but it's still relatively short to find these exceptional events. So the uncertainty is also very large. And given these uncertainties of the observation-based estimate, of this estimate, they overlap largely. So they don't disagree. Although one says 1 in 1,000 and one says 1 in 500 years. And here, just you can also see how the return period of record-breaking events increases if we put on a different margin of by how much the record should be broken. And there are only 2 simulations here where the old record is broken by more than 0.275 or 0.3. So this return period has extreme uncertainties. So don't take this number for take this number as a certainty or something. And then we were also wondering, we have these jumps in models, but we are all aware that we have some models that have warmed in the past much faster than the observed warming has been, so these so-called hot models. And we are wondering if we get these jumps in the models just because we have hot models that have a very large trend and that hence creates such jumps. And this is where we looked into these kind of distributions. It's a bit of a complicated and messy plot. On the x-axis, you have the warming trend in the model, which we calculated in the same way as we did in the observations. And here's the temperature variability or variance that we also calculated in the same way. And then we calculated, and here the autocorrelation is 0.4. And the models, here you see models that are close to that autocorrelation, and you see them distributed according to the warming trend and temperature variability. And the background is the theoretical return period that we calculated again from 100 million time steps time series. And you see that we have models with a large trend, we have models with large variability, and the big dots are the ones that simulate jumps of at least 0.25 degrees. And we see they're not necessarily warm models. Some are even warming much slower than the observations that are here, but they might be more variable, but it's basically a mix of a lot of different things. And then if we add on top of that the different autocorrelations, so here are the models that cluster around 0.3, 0.4, 5, and 6. We see that we have jumps almost everywhere, and that sometimes it's because of a large trend, and sometimes it's because of large variability, or mix of everything. So we couldn't identify a systematic thing to say it's just because models warm too much or models are too variable. It can basically happen with a lot of different combinations, which I think is interesting and gives confidence that it's not because of a bias in the model that we see these events, so that they actually can simulate it. And given that they can simulate it, we look then at the pattern as well. So this is here, you see the anomaly compared to the 30 years preceding the event in SSTs. And again, from observations from NOAA data, then one CMIP6 model from the Ken ESM, one GFDL model, and one CASN2 model. And what is interesting in these plots, I didn't put all 11 here, it would be a bit too much, is that we always have an El Nino. So to get such a jump, an El Nino is absolutely necessary. And often it gets very warm in the North Pacific and North Atlantic, which I've found surprising that this coincidence, that's a similar pattern as in the observations, because we don't have this aerosol effect here. Because in the prescribed scenario that we used, 585 or 370, we don't see this strong aerosol decline that we saw in observations. So, but still, it's these regions that show often very high SST anomalies. Not always, but often. But yeah, El Nino is a necessary condition. And then we thought, given that we have relatively similar patterns, if we have a good return period that fits to observations, we can look what happens afterwards and see if the models are still consistent with the observations. And we see that in all simulations, the SSTs stop to be record-breaking between May and September in the year after the jump. So this is in observations, and here are some models. And then we see the agreement. So here's again the daily resolution. In the observations, it stopped to be record-breaking in July, so just between May and September. So for now, that means until that point, in the models, it's just internal variability, and the observations do the same thing. So it means it still could be an event that has been caused by internal variability. And I want to emphasize that I say it could be because at this point, I think there's no evidence that it has only been internal variability. There's no evidence that it has been a system shift and warming has accelerated more than we anticipated it would accelerate based on increasing emissions, because we know warming has accelerated and will accelerate if we continue to increase emissions. And I think Audrey Menier was in the audience, and she had this nice paper showing in observations that it has accelerated. But the question is, has it accelerated even faster than we expected? And then we also look what happens in the years afterwards, so the 10 years following the jump, which are the green lines here in each of the 11 simulations now. And what we see in most cases is that SSTs return at least briefly to pre-jump levels. At least they touch it somewhere, and basically the gap that was created is closed in the years following the jump. That happens in 8 models, but in 3 models, we see that the gap that was created kind of stays there and temperatures don't go back to pre-jump levels. And what is special about these models, I highlighted them here, is that they all have very high climate sensitivity. So we have the Canadian Earth System model, which is one of the very highest, and the IPSL model, which is also on the higher side. And we were wondering, given that these have a high climate sensitivity, what happens, and they create this gap, could this be a sign that there's some unexpected acceleration? And we looked at the time series compared to the multi-model ensemble mean. And here are the 3 simulations. So the CAN ESM compared to the ensemble mean in orange, the second one from Canadian Earth System model, and the IPSL. What we see here always is the jump indicated by the dashed line. The temperatures briefly shoot up, then go down, but they don't completely go back to the pre-jump levels. But on the long term, they go back to the ensemble mean. So even in these simulations with a high equilibrium climate sensitivity, we don't see a jump to a higher warming level or something. We just see that it goes up, but then over time goes back. Sometimes it takes a bit longer, but goes back to the ensemble mean. So we were then also wondering what happened in observations. So we had these 8 models where temperatures go back to the pre-jump levels by September of the second year afterwards, and the high ECS models where they never go back, but still go back to the long-term warming trend. And in observations we had here in November, temperatures coming back over an entire month to pre-jump levels, 2 years after the jump had started. And in the 8 models, it happened latest by September. So it happened a bit later than in most of the models, but it happened. So it's just a small indicator. It's by no means any proof, but it suggests somehow that the trend in the observations might be a bit higher than in most models, and that the TCRE might be higher and the equilibrium climate sensitivity, but not as high as in the very high or in the hot models with a very high ECS, because temperatures returned briefly. And we have this paper, and I think most of you have seen it lately because Linus has given a presentation about it, where we show that the models overestimate the sea ice in the Southern Ocean, underestimate the sea ice in the Southern Ocean, and then underestimate the future warming, and have a 2-week transition from a already mild state to a warm state. And I think you have seen the presentation. Otherwise, there's the recording online and the paper, so I won't spend much time on it. But now, given that models have a similar pattern and that the development after the jump is similar to what we've seen in observations, we were wondering what happens in these models after such jumps on the longer term, and what should we expect in terms of warming for the next years, if, and I still say if, this was really natural variability. I want to emphasize again, I don't want to make the point that it was, but that it could have been, and that there are indications that it has been, but it doesn't mean that there's not something else happening. There can still be something else happening. The different options still on the table, and I think we have to work out to find out which one is the correct interpretation. So in the future, we're wondering either if warming has accelerated, we would expect atmospheric warming to continue on a higher line than previously. And I'm just putting linear lines here for an indication. This is a purely a sketch. We know that warming isn't linear, it's increasing, but it's just to make the point that are we going to see now warming at a higher level, or are we going back to where we were before? And then we might expect an hiatus over the next 6, 7, 8 years. And we actually looked at that in the models. And here you see the length of the hiatus, and it's always defined as the number of years over which we see no temperature or we see no positive trend in if we fit a linear trend, we see no positive values, or the linear trend is negative or zero. And in any year that we have in a climate model, the probability of a hiatus exists, but it's relatively small and decreases with length. But if we add the condition that we had a year where the atmospheric temperatures were broken by 0.17 degrees, as it happened in the observations, we see already that the likelihood of an hiatus increases with around to a maximum at 5 years. So to make the statistics of this is, at any given year, we could have 3 years of no positive trend in observations. If we add the condition that we had a record-breaking atmospheric temperature jump, the most likely is 5.1 years already. So over 5 years, no positive trend. And if we then add the condition that we have a record-breaking marine heat wave of at least 0.2, I know observations were 0.25, but to have a large enough sample to make a kind of okay distribution, we lowered the criteria even a bit more. We get this distribution, which indicates that if it was natural variability as in the models, we would expect a record-breaking hiatus of 6.7 years and at least 3 years. So 3 years would be 2023, 24, 25. We're already in 26, so I think we are more or less in that condition already. But it's the question, how long does it go? And now with the maybe super El Nino coming, maybe it's already the end of it, but we don't know yet until it evolves over this year. And just to finish off, the pattern that we would expect in atmospheric temperatures is that we would see no warming or cooling in the El Nino region, because we come out of a strong El Nino and going afterwards into an La Nina condition. And then with teleconnections, we get that in the Southern Ocean and in Alaska and somehow around the tropics in general. And if we want to see where 100% of the models agree after a record-breaking atmospheric event, there's no agreement for all models, but after marine heat waves, there's 100% agreement on the sign in the El Nino region and almost nowhere else. So that would be the talk. I went a bit over time. I'm sorry for that. I hope that was okay. I'll let you read the messages and stop talking so that you can ask the questions.